minus 0.007 with, sorry, it will come down like that. There's an oscillation, and we'll run that. I'll be able to draw for you this picture without doing all the work that we have to do. So one way you can get this picture is do all the steps that we learned and find y prime of t and plot it. Okay? But I can provide this plot of y prime against t without solving anything. So that's the next topic. When I say quantitative response, we still have a new value when it ends up. We still have things like oscillations, okay? But I don't have the exact numbers. But I can do that, you see, I drew that for you just by inspection. Just put a transfer function and immediately predict what y prime against t would look like. Yes, sir.
How did you do that?
Well, that's the next topic. Exactly. How can we do it?
What is the 0.007 number?
It's the new value where y prime ends up as time goes to infinity. We'll end up on that. Unless I did the algebra in my head wrong. Okay. So, how can I say that? A lot of information that we will need, information we will use poles and zeros and what is GU at time 0. No, not at time 0, that is the GU at S. Okay, so we're talking about U, or in the general case Z, that's a step change of G0. This applies to any transfer function regarding a step change to the input for that transfer function. So if I want to find what happens if disturbance D2 did something, I would be working with GD2. If I want to find what happens if the manipulated input did something, I would be working with GU. Clear? So it's whatever Z changes, whatever input changes, I'm looking at that particular transfer function. So, we're talking about Z doing some kind of step change, and what happens to Y prime. Clear? That's the thought. So one thing that can happen is the system can blow up. There's the concept of stability. For linear systems, and remember the transfer function is a linear system, stability basically all boils down to the same thing. Different stability concepts. One is the local asymptotic stability. John has a big smile. Are you doing anything with stability in your research?
Yeah.
Yeah, you'll be very primitive, John. Very, very primitive. So local asymptotic stability, sorry, asymptotic, I shouldn't say local, because for linear systems, something is stable or unstable, but asymptotic stability means that if you make, if the system is stable, with a small change in the input, the system will change a little if it's stable. On the other hand, even an epsilon change, if it's unstable, means it blows up. And for a linear system, blowing up means it goes to infinity. Bounded input, bounded out stability is a related concept. As the name suggests, if there's a bounded change in the input, the output, of course, also bounded doesn't become infinite. Same conditions. The condition for stability is simply that all poles have negative real part. whether they're real or complex, I must have all poles with negative real part. So the first concept, so what will y prime? Yes, and y and y prime are the same thing. You just have to number one. The number one issue is stability. If any, even a single pole, has a positive real part, which means linear system blows up with even the smallest change. Okay. The actual system is not linear, okay? For the actual system, you have concept of local asymptotic stability, which is for the locally valid linearized model, and always same would be translated to local stability. Now for the real system, in all likelihood, real system will not go to infinity. It may go though to a very different steady state, or it may go to a stable periodic solution, or even to chaotic behavior. It may even blow up, okay. So all things possible, but if you have local stability, small changes in the input mean small changes in the output. So if I have even one pole with positive real part, I'm blown. And let's see if I brought my notes. I'm afraid I didn't bring my notes. My last decision means that I'm lecturing somebody didn't bring notes with me. A little bit dangerous, but I'm managing it. I saw some of you low on battery, and I saw some of you haven't already had the field of Excel base. So that means if it's unstable, you make a change like that, and this is what it does, y prime can go up this way, goes infinity that way, or can go up with minus infinity, or can go up this way. Ever increasing oscillation. All these are possible outcomes.
You're saying that if z goes up.
Or if it goes down, that's not. Anything. If it changes from its nominal steady state value.
Oh.
Even epsilon. Okay? Second thing, so on the other hand, if it's stable, we reach eventually new steady state. If all poles have negative real part, also remember that the denominator roots.
You said poles are the roots?
Denominator roots. Did I erase it? I guess.
On the left side.
Yeah, I erased it.
Okay, got it. Oh, I see it.
Yeah, let's make an example. Okay. Yeah, let's do an example. Let's say G0 first is
What is that? Negative real?
So, what are the poles in this case? I have a complex conjugate pair at minus 1.1 plus or minus 12i. These are two poles. Okay? These are two roots. And I have also one at minus 5 and one at minus 10. What are the zeros in this case? 1.5 and minus 2. It's traditional to picture the poles and zeros with X's and O's. So it helps to create a Cartesian coordinate chart. Here we have the imaginary part on the y-axis, the real part on the x-axis, and to put X's for the location of poles and O's for the location of zeros. So here I have poles at minus 1.1 real part and plus or minus 12i imaginary part. So that would be real part about here, let's say, imagine about here, so that would be, here is the minus 1.1 plus or minus 12i. I have another pole at minus 5. I have another pole at minus 10. So I have 4 poles. This is the location of the 4 poles. In this example, I have 2 zeros, one at minus 2, so that's around here. And I also have a 0 at plus 1.5, so something. Poles and zero meaning clear? Okay. So, is the system stable? Yes. All the poles have negative real part. They're on the left-hand side. There's a positive 0. Positive 0 doesn't affect stability. It's still quite useful for control, as we were saying, but it's not blowing up our system. Clear? So, for this one, we can say immediately, for this transfer function, that since all poles have negative real part, we'll reach a new steady state. Okay? So, if all poles have negative real part, if the input reaches a new steady state, so will the output. Now, those of you who took COT with me, although recently I may have run out of time, so I don't think I covered that with your class. Did I cover with your class qualitative response given eigenvalues? No, I don't understand. Okay. Yeah, yours was a class where we lost a lot of holiday because of holidays, right? We lost a lot of class in your COT because of holidays, and so I had to cut some material and I cut it out. Okay. All right. In the past, we have had some previous exposure on that, so there's no connection to me. Yes. But basically, okay, you learn about eigenvalues in COT. Okay. The poles of the system are the same as the eigenvalues you learned about in COT. Let me make quickly that connection. Remember our transfer function, what it is? Remember our transfer function is C transpose Si minus A inverse B e to the minus ds, or gamma I here. And remember, it's a ratio of polynomials times e to the minus ds. What's the denominator of this? What is Si minus A inverse? It's the adjoint divided by what? The determinant. That's a matrix, that's a scalar. If you make this multiplication, the result of the denominator is going to be determinant Si minus A. So the denominator of GU and GDI is determinant of Si minus A. So all my poles will have determinant Si minus A equals 0. Remember eigenvalues. What was the characteristic equation for eigenvalues? For eigenvalues, denominator of T's is determinant Si minus A. We say it from there. That's the denominator of the transfer function. So poles are the roots of determinant Si minus A equals 0. These are the poles. And eigenvalues of A are the roots of the characteristic equation I don't know if Dr. Ladd covers this stuff.
I don't know about that.
Make
But anyway, definitely I covered that. I know I definitely covered that. And the characteristic equation is what? Determinant A minus lambda I equals 0. Those of you who took COT with me must remember that. Daniel, you remember that, right? Well, you can easily, you can show that determinant A minus lambda I is equal plus or minus determinant lambda I minus A. Depends on whether the size is odd or even, if it's a 4 by 4 or a 3 by 3 or a 7 by 7. But determinant of A minus lambda I is equal to plus minus determinant lambda I minus A. Which means what? The roots of this equation are the same as the roots of this equation. So you can say that the poles we're talking about today are nothing else than the eigenvalues we discussed in COT. Okay? So, if we are unstable, if we have even one positive pole, we blow the step change. On the other hand, if we are stable and we have a step change in the input, if my input does something like this one, or this, or even this, eventually reaches a constant value. And my system is stable, I'll eventually reach a constant value. And I can tell you directly what the constant value is. Now, we already know a method you can use to find what is the constant value. What's that? Suppose that I gave you this transfer function, and I told you the input decreased by 3 at time 0. What is the new steady state? How would you find it? Mika. Make what? No. No.
You have to find the
Open.
You take the limit as approaches 0.
Okay. That's, you're running ahead of time. In terms of what we've been doing so far, how will you get it? Although you're quite correct, but
well, to use the dictionary, we have to like split it up into like little parts.
well, we know how to get y prime of t, right? So we can get y prime of t and take the limit equals to infinity. Right? We can find the new steady state. So if z is doing this, y prime will end up somehow, whatever it does,